Good morning, all of you. Myself, Dr. Harale, Assistant Professor, Department of Physics, Sadhguru Kadge Maharaj College, Karad. We are discussing regarding some concept regarding nanoscience and technology. We are dealing with the third lecture of this introductory part of nanoscience and technology. So, in basic concept regarding nanoscience and technology, we have discussed in earlier two lectures, and we are going to discuss the remaining part of that introductory part of nanoscience and technology in our present lecture. So, what up to now, what we have learned regarding the last lecture, nanosystem. What is the different dimensionally materials in two-dimensional, three-dimensional or zero-dimensional, which is we have discussed regarding nanosystem. Comparison of nanometric scale. For example, we have taken that human hair as an example, and we have discussed we have cutted the slices of that human hair and compare with that 100 micron scale to 1 nanometer. What happens with the 1 nanometer scale? Now, third part we have discussed regarding scaling up from nanometric scale. We are going from nanometric scale to a micro or macro level system. Classification of material based on grain size. How the grain size affects and what happens with surface area and other parameters we have discussed regarding that. Nanoscience, regarding some parameters, why it is necessary to study the nanoscience, what is importance of nanoscience, we have already discussed. The scale things, the nanometer scale to meter and more. So things is intentionally fabricated things and non-intentionally fabricated things we have discussed in this. And why 1 to 100 nanometer is important, we have discussed that is major part is quantum confinement or quantum effect we have studied in this part. And lastly we have discussed regarding surface to volume ratio, what happens with this surface to volume ratio when you go for nanometric scale. Now the next part, before discussing the next part, we are going back. What is a milestone in nanotechnology? From which year this concept start, and in what way this nanotechnology is growing? In 1957, Michael Faraday synthesized gold colloid nano-sized particles. This is the first study related to gold nanoparticles. This is from gold colloid nano-size. In then 1950, Oswald, a famous chemist, wrote a book, World of Neglected Dimension, in German. So he has mentioned some concept regarding that dimensions. Again in 1931, Ruska and Knoll developed the first electron microscope, and they have observed the nanometric scale objects by using that. And in this, Muller in 1951 developed a field ion microscope which enabled the imaging of atom from the tip of metallic samples. This is the invention, first invention. You can imagine of atoms from the tip of metallic samples in 1951. Again in 1959, Richard Feynman, we have already discussed regarding this. Richard Feynman delivered his very famous talk, There is a plenty of rooms at the bottom, which pointing out the first nano visionary called as Richard Feynman, giving the concept in 1956. So this is some development in nanoscience. In 1968, Cow and Arthur developed the molecular beam epitaxy technique for layer by layer growth of materials. So scientists are trying to synthesize the material by using different techniques. And in 1968, this Arthur and his co-worker Cho developed the molecular beam epitaxy technique for the layer by layer growth of materials. In 1970, Pikaski demonstrated the quantum size effect, which is QSE, in semiconductors. Again in 1980, what happens? The quantum size effect in CDS and CDSE nanoparticles dispersed in glass. They have studied the effect. In 1981, Rohr developed and his co-worker developed the scanning tunneling microscope S.G.M, by which atomic resolution could be obtained. This was also followed by the family of scanning probe microscopy. So the development of this scanning microscope is started in 1981, which is starting with the scanning tunneling microscope S.G.M. various types. Then again in 1985 the fullerene is discovered. In 1989 the IBM Igler wrote the later IBM using xenon atoms. So like that lithography technique they have used in 1989. In 1991 the Japanese scientist S.G.M discovered the carbon nanotubes. He got the Nobel Prize for that, for the discovery of carbon nanotubes CNTs. And from that onwards there is a much more intentionally development of nanomaterials going on after the discovery of that carbon nanotube. Also in 1919 S.G.M developed the deep paint lithography as another technique for the synthesis of nano patterning or nanomaterials. In 2000 Igler again gives the concept quantum merge using the iron atoms on the copper substrate. The quantum merge is another concept given by Igler in 2000. So what happens with another in earlier case related with quantum mechanics, from which theoretically or basically concept starting with, because when you go for the nanometric scale the quantum mechanics is implemented. Why? Because at this micro level classical mechanics is applicable, but when you go at atomic or molecular level classical mechanics does not work. You have to go for quantum mechanics. That's why the historical milestone in the development of quantum mechanics. So pre-quantum era in 1669 Newton proposed that the light had corpuscular or particle nature. Then again there is a development with in 1690 that light had a wave nature. Heisenberg claimed that in 1690 light had a wave nature. Now Kirchhoff and others studied the black body radiation around 1860. So slowly there is a development in this quantum mechanics. Maxwell proposed in 1873 a theory of electromagnetic waves. So slowly there is a development in quantum mechanics. We are discussing pre-quantum area. In 1803-04, Young performed double-slit experiment which showed that light had wave nature. So people are working on that electromagnetic nature, wave nature, particle nature, like that. So before up to 1803 they are known as a light had a wave nature. In 1887 Heinrich Hertz produced and detected the electromagnetic radiation. So slowly there is a development. Now old quantum theory period. In 1901 Max Planck showed that the energy distribution in black body radiation could be explained properly only if one considered that the radiation was quantized. Quantized restriction. Quantized meaning of that quantized restriction or had a particle nature. So in earlier case they are only thinking that this only there is a wave nature, but here in 1901 Max Planck gives the concept regarding the particle nature of that electromagnetic wave. So electromagnetic wave up to now possesses that the dual nature. What is dual nature? That is a particle nature as well as wave nature. Now in 1905 Einstein proposed the theory of photoelectric effect which proved that the quantum or particle nature was associated with electromagnetic waves. This is another invention which helps to develop the quantum theory. Now quantum effect in 1920 could be explained only when the particle nature of electromagnetic radiation was concerned. If you consider only electromagnetic radiation, then this concept quantum effect could be explained only when the particle nature of electromagnetic radiation was considered. Supporting Max Planck and Einstein theories. Here Max Planck and Einstein given the description or proof or evidence that this waves possesses quantum or particle nature. So this quantum effect is explained that the nature is in particle nature, electromagnetic radiation in particle nature, which support that for this both Einstein as well as Planck's theory. Now in D. Broglie in 1923 argued that the electromagnetic waves are particle photons and finite particles have wave associated with them. So here is a concept of wave particle duality which is given by de Broglie. Bohr atom model in 1913 with a stationary states why electrons should have some fixed energy could be explained with the de Broglie hypothesis. We have discussed regarding the old quantum theory. Before going to that nanometric scale, what happens at quantum mechanics at nanometric scale? Before that, we have discussed the old quantum theory period. Now, we are discussing regarding modern quantum theory period. So, modern quantum theory begins with Heisenberg introduced in 1925 with a matrix mechanics. Schrödinger equation is a famous equation. 1926 gave the confirmed foundation for the de Broglie hypothesis. De Broglie hypothesis we are seeing here that de Broglie shows the wave particle duality or both the nature electromagnetic wave having the both particle as well as wave nature or wave particle duality. So in 1927 that Davison and Germer showed in 1927 that electrons can be diffracted. Regularly spaced atoms constitute multi-slit analog of Young's double-slit experiment. Heisenberg proposed the uncertainty principle in 1928. This marks the beginning of quantum mechanics as practiced now. We are dealing with that. This is beginning in approximately era of 1925. So just was considering the simple example that black body radiation, a black body is heated, it gives out a spectrum as shown in this figure. This figure shows here is the wavelength and here is the intensity. Now the black body spectrum spread over in the range of wavelength, different range of wavelength here, and has a maximum intensity here, showing this intensity with respect to temperatures T1, T2 and T3. These are the three different temperatures. T1 is less than T2, less than T3. That is T3 temperature has higher temperature than T2 than T1. Now experiments on the black body radiation led Stephan in 1879 and Boltzmann, just Stephan Boltzmann's concept to establish the Stephan-Boltzmann law. So what this represents, the temperature increases, the spectral intensity here. Spectral intensity increases and maximum intensity shift to a shorter wavelength. Like that temperature T1, T2, T3 are the different temperatures in the increasing order. Here T3 has maximum, T2 is less than T3 and T1 is less than T2. So higher temperature is T3, then lesser T2 and lesser T1. So here we have observed that if the temperature is higher in case of black body radiation, then it goes to the maximum intensity shifts toward a shorter wavelength. So this black body is proportional to the fourth power of absolute temperature. This is a famous equation. If intensity that radiation intensity of total radiation and T is the absolute temperature, then E is equal to sigma into T raised to 4. This is the equation is known as Stephan-Boltzmann law. Now why we have taken this equation? It is found that this formula holds good only for short wavelength side of the spectrum. Therefore, the scientists continued their effort to find out the suitable equation which would be able to give or simulate the complete spectrum. We have seen only a limited spectrum, but when you validate the equation, you have to consider the total complete spectrum. That's why Village and Jin arrived at an equation E lambda is equal to 2c lambda raised to 4 kt, where c, here c velocity of light and K is a Boltzmann constant. Now this equation could explain the long wavelength side, longer wavelength side here, longer wavelength side. But what happens in case of black body spectrum? However, it fails at shorter wavelength. So this explains only a longer wavelength. This equation validates only a longer wavelength, but it fails to explain at behavior at shorter wavelengths. Now, thus, none of these equations were satisfactory to explain the black body radiation over the entire range. Now, this mystery continued until the Planck proposed in 1901 formula E lambda is equal to 2 pi h c square divided by lambda raised to 5 into 1 upon e raised to sc by lambda kt minus 1. This is a modification in the equation to cover or to explain the to validate the equation in case of shorter wavelength. So this is a starting of that mechanics, quantum mechanics, development of quantum mechanics, and which correlate with this nanometric scale. So before going to details, we have to first see what is dimensionally distinguished between that materials, nanometric materials like zero-dimensional, one-dimensional, two-dimensional, three-dimensional. What is that dimensionally distinguished between that materials or classification of nanomaterials? As already we have seen, if you consider a block of metal having the coordinates x, y, z coordinates, which is a three-dimensional object, we can call it as three-dimensional. When you cut a one-dimensional in a nanometric scale, then it becomes a 2D material because it's one-dimensional in the range of 0 to 100 nanometers. We are considering the thickness of that film. So, example, ultra-thin film is a two-dimensional. Again, you reduce the another two-dimensional, keep to only a one dimension, then this will become two dimensions, other two dimensions, or in nanometric scale, restricted scale, and only one dimension present, which is called as one-dimensional materials. For example, nanorod, nanotube. That's the example. When you restrict or the other three dimensions, then it becomes this cube become a cluster or nanoparticle, which is known as zero-dimensionally. So when you reduce the dimensional, x, y, z at the three dimensions, when you reduce that dimension, you will find that a metal block is get converted into 2D material. Then again, when you restrict the other two dimensions, then 1D material, nanorod, nanotube, and again you reduce the three-dimensional, total three-dimensional, then it becomes a cluster or nanoparticle, which is called as zero-D. So that's why at least one of its properties is size dependent. Insulating, we have taken the initially block of metal is insulating block, but when it become a nanorod or a nanotube one dimension, it become conducting. That's the emerging new property due to nanometric scale. So what is three-dimensional? Three-dimensional material. Bulk material are the material that are not confined to the nanoscale in any dimension. So there is no any restrictions on this dimensionally. These materials are thus characterized by having three arbitrary dimensions above 100 nanometers. So just consider this box having three dimensions and coordinates x, y, z coordinates. Bulk nanomaterials can be composed of multiple arrangement of nano-sized crystals in different orientation. Here you can find the orientation is different. Material possesses the presence of features at the nanoscales. The arrangement of nanoparticles, bundle of nanowires and nanotube, we can find out which made the three-dimensional material. Here is the example of three-dimensional materials. Nano flower, you can see the three-dimensional nanostructure, which is the three-dimensional nano materials. So there is no quantization of particle motion occurs, that is particle is free, which is a three-dimensional material. Now what happens with two-dimensional materials? If you consider the two dimensions, there are two dimensions are not confined to the nanometric scale. So 2D nanomaterial exhibit plate-like structure. Here only thickness is in the range of nanometers, are very small and negligible. Other 2 dimensions present here, that's why it's called as 2 dimensional. So 2 dimensional nanomaterials include the nanofilms, nanolayer, nanocoating, like that. It is you can find out Lx is length, Ly is a length in this dimension, and the thickness another dimension is very small. So thickness of this film is very small, less than 100 nanometer. That's why we can call it as this 2D materials. So third dimension is negligible or very smaller range. That's why we are neglecting the dimension. That's why we are calling this object or material 2 dimensional. Here is a graphene sheet. Is an example of 2 dimensional material. Here is a nanoplates. Here called as 2D plates. Is an example of 2 dimensional nanomaterials. Now, what is 1 dimensional? 1 dimension that is outside the nanoscale. This leads to a needle shape or needle-like shaped nanomaterials. So only the restrictions in case of 1 dimensional materials, restrictions from other 2 dimensions, only 1 dimension you are allowed. That's why this diameter of that nanometer in the range of nanometric scale. Length in terms of micron or higher length, L. So only 1 dimension is allowed and other 2 dimensions are already restricted. That's why this material is known as 1 dimensional materials. So 1D materials includes nanotube, nanorod, nanowires, like that. So here is a general example carbon nanotube. So this multi-wall nanotube or single wall nanotube is an example of 1 dimension. Only 1 dimension is allowed and other 2 dimensions are restricted. In case of 2D, only 2 dimensions. Here this one and this one is allowed and only a single dimension is constructed or negligible, very thickness is very less. So here the diameter is very less and less than 100 nanometers. This is a transmission electron microscopy image which shows the actual image of that carbon nanotubes. So what is zero-dimensional material? Whenever all dimensions are measured within the nanometer scale, so there is no dimension which is called as or known as zero dimension. So generally the restricted in all 3 coordinates x, y, z or 3 dimensions x, y, z. That's why this is called as zero-dimensional material. So present this in a spherical shape. The most common representation of the zero-dimensional materials are cluster or colloids from nanoparticles, nanoclusters or quantum dots. Here you can find all the dimensions x, y, z are in nanometric scale, very small scale. That's why it is called as zero-dimensional materials. Example, quantum dot is an example. Now here in this figure you can find out 1 dimensional. This is only allowed in z axis and the other 2 dimensions very less. Here in case of 2D material, only a single thickness is in the range of nanometric. That's why it is a 2D material. 3D, no dimension at nanoscale, all the dimensions at microscale. That's why we can easily distinguish between the zero-dimensional material, 1-dimensional material, 2-dimensional and 3-dimensional materials. So in case of zero-dimensional, here we have taken the particular example which is quantum dot. When you change the size of that, there is a change in color of that. This is the emission color of quantum dot. When you illuminate with UV light, you will find the different colors. Why these different colors? Because due to this change in size, which is responsible for getting the different color. Now common features of nanoparticles. Nanoparticles be amorphous or crystalline, be a single crystalline or polycrystalline material, exhibit various shapes and forms, maybe occurs in zero-dimensional, 1-dimensional, 2-dimensional or 3-dimensional. These are the common features of nanomaterials. Exist individually or incorporated in a matrix, be metallic, semiconducting or insulating behavior. So it is important to study the surface to volume ratio in case of nanomaterials. Here we can find out the example, granular sugar and sugar cubes. So maximum surface area and it required the number of atoms on this surface gives the better surface area. That's why the nanometers, we are interested in nanometers because this provide the highest surface to volume ratio. Now size dependent properties, some properties are related to size like chemical properties, thermal properties, mechanical properties, optical properties, electrical and magnetic properties. These are the size dependent properties and these are particular cases for that properties. Now we are going to details with that nanometric scale, which starting with that atom which atoms comes together forms molecules, molecules comes together forms a cluster, and cluster forms a nanocrystalline or nanocrystals. So this is a semantic representation for the various states of matter, and the basic phenomena occurs to that nanoscale is quantum mechanics. This quantum phenomena, quantum confinement effects, we will discuss in our next lecture. So we have discussed regarding the quantum dots. This is the UV illumination on that quantum dots, and which reflects the various colors. Why this color occurs? Due to the size dependent properties, and we will discuss the remaining part in our next lecture. Thank you.